Okay, this is in two parts because who knows why. So, when we have H plus times OH minus, it is always equal to 1 times 10 to the minus 14. So if you are given 1 times 10 to the minus 4, and you wanted to solve for your OH minus, when the coefficients are 1, you just have to make sure the exponents add to minus 14. So the missing OH minus is 1 times 10 to the minus 10. So it's 1 times 1 is 1, and minus 4 plus minus 10 is minus 14. So that's the simplest case and what you're going to get probably 90% of the time. But if the coefficient is not 1, you're probably going to need to use your calculator. So if I give you 2 times 10 to the minus 5, well, that's not a 1, so we're going to have to do some math. So we just solve this equation for the H plus. So take the 1 times 10 to the minus 14 and divide it by the one we have. So we have 1 times 10 to the minus 14 divided by 2 times 10 to the minus 5. Now, if you do not have a calculator with scientific notation, that's simple to do scientific notation. You divide the numbers. So 1 divided by 2 is 0.5. And then you subtract the exponents. So times 10 to the minus 14 minus a negative 5. So we have 0.5 times 10 to the minus 9. That's not proper scientific notation. So when we move the decimal, make it proper scientific notation, that number is small. So we get a more negative exponent. So we get 5 times 10 to the minus 10. Now if you have a calculator that does scientific notation, remember it's that EE button you use for the times 10. So you would type in 1 EE, and then whichever button makes a negative number, and then 14, divide it by 2 EE, make it negative, and 5. Okay, now, acids have more H plus, bases have more OH minus. When they're equal to each other, you have a neutral solution. And from this, we can do pH. pH is section 8.4, and it has a weird looking formula there. pH equals negative log of the hydrogen ion concentration. That's where the H in pH comes from. It's actually the electrical potential. You don't need to worry about that. Now, you want your H plus in exponential form. 0 up to 7 is going to be your acids, 7 is your neutral, and then above 7 to 14 is the base. Now, when you have the H plus, you can find the pH. And again, when that coefficient is 1, it's really super easy. When the coefficient is 1, all you have to do is take the exponent, make it positive, and boom, there's your pH. So look, we have H plus of 1 times 10 to the minus 5, so pH is 5. H plus of 1 times 10 to the minus 8, so pH is 8. So that first one that I used green on would be an acid, and the other one would be a base. Now, when the coefficient in scientific notation is not 1, and I have a lot of stuff written here that you don't actually need, which is why I crossed it out, just use your calculator. You can actually use that button that says log, L-O-G. Some calculators like you to hit log first and then the number. Some like you to hit the number first and then hit log. You've just got to experiment with your calculator. Now, if you look at these, when we had 1 times 10 to the minus 5, our pH was 5. But when we have something else times 10 to the minus 5, it's always going to be 4 point something, so just a little bit less. We had 1 times 10 to the minus 8, and our pH was 8. When we have 9.2 times 10 to the minus 8, it's 7 point something. So you can always still use that exponent to estimate. Now, Arrhenius acids and bases. This is a way to define acids and bases. This puts us back in 8.1. And acids contain hydrogen ions, and bases contain hydroxide ions. This is an older, actually the first way they defined acids and bases, and it's still true, but we have another more modern definition that includes more substances, because bases on this was really limiting since it only included the metal hydroxides. Now here's the modern definition, Bronsted-Lowry. It defines acids as hydrogen ion donors, which really is not anything different. It's just a rephrasing of the Arrhenius definition. But bases are now a hydrogen ion acceptor. This way it's going to include everything that was included in the Arrhenius definition and some more. But we have to see this equation so that we can see who is donating and who is accepting a hydrogen. So what you're going to be doing is you're going to be finding pairs. You're going to be finding the species on each side that are only different by one hydrogen ion. So NH3 accepts a hydrogen and becomes NH4+. That's what made NH3 the base. And water donated a hydrogen, so it's the acid. Down in the other one, HCl donates the hydrogen, so it's the acid. And H2O, with H3O+, is accepting a hydrogen, so water in that instance is the base. Now the strengths of acids and bases. Acids and bases are electrolytes. So just like electrolytes, it's strong if it completely ionizes, and it's weak if it only partially ionizes. Now, reactions of acids and bases. This is also going to review some things we learned in Chapter 5, because the reactions that we learned in Chapter 5 are the same reactions here, just we have acids and or bases as reactants. And we're going to look at three types. First one is acid plus metal. And this is a single replacement reaction. Remember, in a single replacement reaction, we have one single element plus a compound. So the single element is the metal, in this case aluminum, plus an acid. Here we have hydrochloric acid. Okay, so Al plus HCl. Al is the single element. It's a positive ion, so it's going to replace the positive ion, which in this case is H. When H is by itself now, remember H was diatomic, so it has to be H2. So when we put aluminum and chlorine together, we have to use their charges. So we look on the periodic table and find that aluminum is a +3 and Cl is a -1, and we crisscross charges to get the subscripts. Then we have to go through and balance this equation, which I did wrong. I can see that now. This right here in front of the H2, I don't think I can write anything here. This in front of the H2 should be a 3, and this one here in front of the AlCl3 should be a 2. And our next type is an acid plus a hydroxide base. And this one is a double replacement reaction. So here's an acid, H2SO4. and a hydroxide base, sodium hydroxide. So sulfuric acid and sodium hydroxide. So we have H plus and Na plus, those are our two positive ions. Now H plus was with SO4 2 minus, so it's not going to be with it. On the product side, give me a second there and I'll get it erased. It has to be with the other negative ion. So H plus is going to be with OH minus. And Na plus is going to be with the SO4 2 plus. See, the negative ions traded. So after we figure out which ions go together, we need to crisscross charges to get our formulas. So we get HOH, which is another way of writing water, and Na2SO4. So to balance that, we need a 2 in front of the sodium hydroxide and a 2 in front of the water. So we have an acid and a base. And this is a neutralization reaction. We make a water and we make a salt. And a salt is just an ionic compound. Now our third type of reaction, sorry for making you dizzy here. This time we have an acid plus a base, but the base contains either the carbonate ion or the bicarbonate ion, either CO3 2 minus or HCO3 1 minus. Okay. So a good example of this is vinegar and baking soda. And so vinegar, HC2H3O2, hydrogen and the acetate ion, so that's acetic acid. Notice that's a polyatomic ion. And then we have baking soda, which is sodium hydrogen carbonate or sodium bicarbonate, which is NaHCO3. So we've got double replacement again. We keep our positive ions, H plus and Na plus, and then switch our negative ions. But this time, instead of getting water in a salt, look what we get. We get H2CO3, carbonic acid, plus a salt, sodium acetate. Now, carbonic acid, H2CO3, is unstable. It's what you have in a soda. And then you open the soda, and it releases the carbon dioxide gas. So as soon as you make H2CO3, it decomposes. And what you're going to get is water and carbon dioxide. Carbon dioxide is why you see the bubbles and why it's cool if you mix vinegar and baking soda. And that's going to happen anytime you've got that CO3 in your base. You're going to make water and carbon dioxide, and it's going to bubble when it reacts. Now the last section of this chapter (8.6) is on buffers. Now, a buffer is something that resists pH change when a little bit of acid or a little bit of base is added to it. And blood is a really good example of a buffer system. There's a health note about that. So how do you make a buffer? You take a weak acid and mix it with a salt that has the same negative ion. Or you could take a weak base and mix it with a salt that has the same positive ion. That way you have an acid and a base already in solution to react with whatever comes into the solution. And we are finished. Hopefully these notes work.